All right, so we can get started here. So hi everyone. So my name is Otman, and this is David and Yambo. We're all principal data engineers, scientists, MLE at Spectrum, and we're going to be telling you a little bit about how we streamline our data and machine learning life cycles at Spectrum to via programmatic workflows, so that we can scale our solutions and our iteration process. So with that, let me get started. So I will describe a little bit the problem statement we are trying to, the problem we're trying to solve, and then go through how we select our data for labeling, and then how we ingest it into our feature store. And then we'll go through our model iteration pipeline and then solution pipeline before we kind of close it out with like the conclusions of what we do, why we do what we do. So first, let me just give you kind of a brief overview of what Spectrum does. So you probably heard it earlier in the day, but essentially we have an API, and we have text or audio that comes through with its metadata, and we serve about 20 or so behaviors or solutions. These are operating in 20 languages, more than 20 languages. And they are very fast, so the inferencing time is very fast. And all of that data that goes through is stored into what we call the data vault. So this is where we keep all our data. It is accessible. We'll talk more about it in a second. But then from that data, where all our clients essentially data gets stored, we can sample from it so that we develop and iterate on our solutions. Once we sample from that data so that we label it, we use it as a signal for our machine learning models. So we store it into our feature store. Kind of that's where all the labeled data is. And then this feeds into our classifiers that we train so that we deploy again along with our solutions logic and rules into our API. And then kind of this circle keeps going around. So what I wanted to tell you, and the team here, what we wanted to tell you about is how we moved a lot of these processes from manual, one-off, ad hoc kind of steps into more programmatic workflows that enable us to essentially iterate and develop and release solutions a lot faster. So with that, let me get into a little bit more details. So data comes into the data vault, as you can see in the middle there. And then, so each one of these boxes we'll be talking about in this talk. So the first box is the sampling, and the sampling from our data vault to collect all the data that we send out for labeling. So it goes through the labeling process, it gets stored, labeled data gets stored into our feature store, then we split it into the classical splits that get used into our model training pipeline, then we configure the solution and then deploy it. We'll come back to this diagram at every stage so that we remind you a bit about the workflows that we have in place. So first, why are we doing, or why are we building these processes? So essentially, the manual tracking and development of solutions does not really scale once you start doing them by hand. And typically, data scientists love using kind of notebooks. And if you have like few models that you have to maintain in production, that's tractable. You can keep essentially on spreadsheets versions of your data, versions of your tags of the code that trains your model, and then kind of keep everything neat if it is a matter of like a handful of models. But in our case, I mentioned we have 20 solutions in 20 languages. This is like hundreds of configurations that need to be tracked. You can't really do that by hand. So this is where we're developing solutions that will enable us to have things like lineage, like versioning for like our models, our data comes in very important, especially if you want to track essentially what you've done, track the lineage, have the ability to reproduce any solution that you have in production at any given moment of time. You know exactly how to do that based on the logic of the configuration of the solution. And then also, if you want to emulate the rules that you have in production locally, sometimes these rules can get quite complicated. Many classifiers can be used together to produce a solution, and doing this by hand, trying to emulate this, can be quite taxing and error-prone. And then the last bit is standardization, so that we make sure every team member is following the same exact processes to essentially deliver the solution, sample the data, and so on. So that's kind of like the why we're doing this, or the problem we're trying to solve with these processes. And just because we are using this framework Streamlit for our web app, like kind of front end, it's worth like kind of pausing a moment to talk about it. So as data scientists, generally you don't have expertise to develop your own apps. So typically what you try to do, and you need a lot of them, especially if you want to move away from your notebooks. So typically the process of asking your dev team or your tools team to kind of build an app for you is pretty taxing. Instead, and it's really a distraction from your core work, that you typically have data that you want to process or analyze or prepare for your training. So having an easy way to essentially develop a web app or a front end to your process is that you can kind of do with the tools you know. Typically Python for data scientists is pretty nice. So that's why we kind of moved into Streamlit. So all the apps we will be showing are the front end piece of them are all based on Streamlit. So let's talk about data selection. That's the first kind of step, is you have data sitting in the data vault, you want to sample from it. So generally for good AI solutions, you really need high volumes of data that are of good quality. And for us at Spectrum, we process about 500 million records a day. So this is hundreds of billions of records that we have stored in our data vaults. So we typically take millions of these data to be sent out for labeling, and we have to have very tight quality controls over how this data is labeled, curated, and then ingested back into our feature store in a versioned way. I mean, you can imagine this takes thousands of hours of collective teamwork to get this data labeled so that we can feed it into our models. And bit of a delay. Yeah, so we have this framework that we use essentially to kind of sample first, and I will show you an example in a second on how we do that, just to illustrate one of the steps. But the basic idea is you have kind of proactive analysis where you go into your traffic and then you see trends that are covered and not covered, and then sample from the things that your models currently don't cover, and then pass it, send it back, send it out for labeling. And typically you create Jira. The whole process is automated, where you would create Jira tickets, you store it into S3, and this data that is in S3 gets picked up and sent out for labeling. To illustrate this, so for example, here I have just an example of essentially embedded text data that is projected into a 2D plane, and the green dots is new traffic data, while the circles is our feature store or labeled data. And what it shows in this example is that we have kind of good coverage between two categories. This is a binary classification, so what's toxic and what's non-toxic. But typically what happens is over time you get new trends of data, and when you run kind of inference on them, you can see that in this case we don't have any coverage on that blob that is on the lower side of the slide. And actually the coloring means how confident we are in the classification. So green means we're very confident, and that's kind of what is shown in the upper side. But then yellow and red, that means we're not very confident. So typically what we would do, part of this sampling process, which is automated, is you just essentially pick these samples or data from it and then send it out for labeling. Yeah, and this is an example of how we do that. And then this is just kind of a look of at the web app, the Streamlit-based app that essentially walks you through all the steps that we do, so that we make sure we have a good coverage of data from different clients across languages and so on. So I talked a little bit about the data sampling size. Now I will let David talk to you about how data is stored in Data Vault and what technologies we use there, and then also how do we register the labeled data that comes back to us into our feature store, which is really just a labeled data store, and how we version it and use it. So let me pass it on to David.
Thanks, Atman. So just to reiterate, the Data Vault is a key component within our data infrastructure. It serves as both a catalog and a data store for all our labeling data. our two main sources of data within the data vault are our customer data that we get, and also then we have data scrapers that are able to retrieve data from third-party websites. So all our customer data is scored and classified when it hits our APIs, and from there then we have a ingestion pipeline that will scrub it of any personal information and eventually store that into both S3 and also into Snowflake. Every file too as well is also catalogued in Data Vault, which I said it also serves as a catalog. Then on the right hand side we've got our data scrapers, and we have different scrapers that have been built to retrieve data from public websites, also from Twitter, Reddit and social media accounts. In this case we have a batch-based process that will classify and score the data before we store it in Snowflake. There's no PII masking in this case because it's public accessible data. So the feature store, like Oppen described, that's basically our storage of all our labeled data within Spectrum. So this is an example of what data looks like for us within Spectrum. We have a text record which could be coming from a chat. It has, in this case, it's human labeled data, so it's got a classification here to be true. We also have a lexicon. A lexicon serves as the contract basically between a labeler, our data scientists, and our classifier. It's the rules that will define whether a particular behavior ends up being true or false. So this is typically what a record looks like before it's ingested into our feature store. We also have a source column. The source column ties back every record to a file in our Data Vault catalog, and this provides us a way to get lineage and also to perform analysis to figure out if we're retrieving too much data for labeling from different sources, different verticals, different customers, etc. When it comes to ingesting data into the feature store, there's three main buckets that data is moved into. We've got our train set, our validation set. Our validation is done post-training, which I'll describe later on. And also then the last step is run on our test data set. Our test data set, our data scientists can see. So it's the final step or set of data that we would test out our solution on before we would deploy to production. So typically the train set will be 80% of our data, validate and test would be 10% of the data. For the engineers in the room, just a little bit about the design here. A labeled file lands basically into our system at the completion of the human labeling process. So that data is stored in S3. We've then built out a feature store application. It's a web application that performs transformations, etc., validations on the data before eventually storing that data in both S3 and Snowflake. So within Spectrum, on the data engineering side, we're primarily a Scala shop. We also have Python 2 as well, but when it comes to creating web applications, we use Scala and Play. So Play is the web framework of choice within Scala. So if you're familiar with Java, you'd almost like the Spring version of the Scala ecosystem. We store all our data, like I said, in Snowflake. So typically what happens is we get a file, we load it into a temporary table in Snowflake. We then run SQL on that table to perform validations, transformations, etc., before finally loading it into an append-only master table. So I think that describes the ingestion process. Then when it comes to using it, Oppen has already described the usage of Streamlit. We have found it to be a great tool to allow us to build applications for our data scientists within our data engineering organization. It allows us to quickly stand up these user interfaces without having to play around with HTML and JavaScript and all those kind of things to create UI. So we've built query APIs that interact with our feature store application via a thin Streamlit application. So when it comes to ingesting data into any system, having robust validations and transformations is really important. We've learned from our mistakes here where we had a previous incarnation of this. We didn't have the same level of validations. Bad data got into the system. It gets very hard and it's a laborious process to be able to correct that. So we've really invested in having a robust pipeline when it comes to ingesting data. So like I described it already, we ingest the data into a temporary table. We then perform a series of validations on that data. Basically, our feature store application is running SQL against Snowflake on our data to determine whether Booleans are Booleans, whether we have no nulls, all those kind of things are done before eventually is stored into S3 and Snowflake. We also perform transformations. So for example, text can come in with punctuation, emojis, that kind of stuff. We have a utility that can strip all that out and create a version of the clean text, which is then available to the data scientists for when it comes to training after this step. We also have split determinations. Like I described earlier, the split determinations can be trained, validated, or tested. We need to work out what those are. If a record was previously stored in the train set and we then relabel that for whatever reason, if it's a new version of the lexicon, we could relabel that data needs to in back up in the train set again. So there's a lot of various steps that go on here to get the data reliably into our feature store. Versioning and immutability is a really important part of the design. When it comes to lineage and figuring out what we did when, figuring out how we arrived at a particular classification, we need to know what versions of our feature store we were using when it came to training. So every time we ingest a file into the feature store, we create a new version. You can see there after we ingest a file and we bump up the patch version and we add a timestamp. Typically what happens is we will ingest data as part of an iteration, which could be a couple of weeks. Once we've completed ingestion, we will create a release candidate. Once validation is complete and we're ready to deploy to production, we'll then code a release. And at that point, we have an immutable version of our feature store, which we can reference at any point down the line to understand exactly what we had at that point in time. Lastly, because all the data is stored in Snowflake, we have the ability to create some analytical reports to determine what kind of data that we have within our feature store. So we have all those analytics. Snowsight is a tool that we use within Snowflake. It's a UI that allows you to create pie charts, bar charts, those kind of things by writing simple SQL statements. So I'm just going to switch over here now to do a quick demo of our Streamline application around the feature store. So this is an application that we've written. This is the user interface for our feature store. So this is our ingestion screen. Basically allows you to specify a lexicon, a version, and then an S3 location. You can also override the splits. This can also be invoked programmatically. So everything that we have here, the backend is a gRPC endpoint. So another tool could interact with it without having to go through the UI, obviously. Just to show what we have around our label data sets. So every time that we ingest a file into our feature store, this is almost like a catalog of everything that we've ingested. So we take the data from the input location, we copy it over into this bucket. It's a read-only bucket, and we also store some metadata around the file that was ingested. So if anything ever happened to our Snowflake database, we could just replay all these files from start to finish and we'd be able to restore things if we had some sort of critical event like that. Just to show then the versioning, every time that we ingest, we create a new version of our feature store. We have different types of release types. We've got a release candidate, and our pre-release. So the data scientist here can go in here, query this, and understand what was ingested when. So I'll describe later on a little bit more around how we can query that. But that, I think, should be a good overview of our feature store application. So now I'll hand it over to Jambo to describe our model training process.
Okay, cool. So I'm going to be talking a little bit about the model training process and how do we streamline it at Spectrum. Before that, I want to take a step back and paint a picture in an ideal world in which once we have the data ready, it immediately goes into ML model development. And then the data scientist or ML researcher can do whatever they want. They build a really good performing model out of this process, and then it directly goes into operation. And then the operation gives feedback to the ML model development process to see if there are any other tips we can make improvements on the performance, which gives another direct feedback to how do we sample the data and how do we prepare our feature store to better improve the whole process. So this is, of course, an ideal world. The reality is always not so rosy. So what happens is there's this conflict between what researchers or data scientists like to do and what engineers prefer. So on one hand, researchers and data scientists like to optimize for performance. So the tools they like to use are usually very customized. They see this newest trend that's available on GitHub, they import a library, and then they just play around in their notebook, get really good performance, and they build a model, give it to the eng team, and then the eng doesn't know how to deploy in the system because the library is not available. So there's always this back and forth process of figuring out what to do exactly in production. And then on the other hand, the engineers really like to have a single deployable artifact that they can directly plug into the system, but that's not usually what comes out of the DS process. And then so that's one source of conflict of whether like the time to production is not always linear. The other thing is that in the very early stage of building a model as a part of the product, you do start with a very manual process. You figure out what heuristics you want to use. You start with very little data. The data quality is not always good. And then you kind of iterate on the process until you have good enough amount of data. And then you work on the model architecture optimization. And then you do a lot of work around that area. And then as the more data you get in, you actually kind of slow down on your model architecture experimentation. And then you can just keep using the new data that comes in, and then you can retrain the same model, and then you can actually see pretty linear improvement on the performance that way. So this is kind of the state that Spectrum is in when I joined about 6 months ago. So we made a decision that we're going to focus on the model training phase and deployment so that we can give the tools back into the data scientists' hands so they can train something and directly put into production to minimize the manual effort. And then so kind of go back to this diagram again. I'm going to be talking about the lower right half of this diagram, which is once we get data, we train a model, we have a model, we validate it, and then we want to directly plug it into the production system so it's serving ready. So I'm going to go through a few modules here. On the left-hand side, you're going to see our thought process, and then more like in the ideal world, this is the best practice and how you want to do it. And then on the right-hand side, I'm going to talk a little bit about the implementation because this is like a trade-off process we're going through, and then we're also like building the first phase of this automatic ML training pipeline. So so you will see like our trade-off process there. So the very first thing is that we want to package our tooling and everything we have into the single place. So like, of course, you know, there are open source code on GitHub that you can just call sklearn and then you can train a classifier model and everything. But you know, you're building a product in a company that has to be compatible with whatever can be put into a production like serving pipeline. So we have our, you know, ML tooling package, our internal library that has open source, but also has a lot of customization. So we want to first of all put that into a single package. And then we also want to have a record for the models that we are using. Where does that model come from? What are the model's downstream implication and stuff? And then, of course, we want to be mindful about where the data is sitting, what resource we want to use. So in terms of the implementation, so we use Docker to package everything. We make sure that we have version control of our libraries. And then feature store is the single source of truth of our training and validation data set, which is David just talked about. And then for model registry, we don't want to reinvent the wheels. So we went to weights and biases and take advantage of their model registry function. And then, of course, like we started planning on GPU usage very early on of this pipeline. And And then so once we have the packages ready, we want to make sure that we are doing rigorous testing for our pipeline. So one is the data test. So like, for example, are there missing values in our feature store? Are there empty values? Are there extreme values? Are we expecting a Boolean, but in reality, we're getting a string? So there's a lot of data testing you want to be mindful of. And then, so secondly, you want to do functional testing. So like, are you using the right loss function for your prediction? Is the prediction layer, is the deep learning layer actually generating a probability distribution? And then, of course, you want to make sure that the model that you're launching is feasible for the business application. For example, at Spectrum, we want to fit our prediction into a very short period of latency. So like, is our model actually able to spit out a prediction in a very short period of time? So that's pretty much what we did. We make sure that we have rigorous unit testing. We have load tests for how much memory our model used. And then we also make sure that the generated artifact of the prediction model is actually spitting out probability for whatever the input it takes. And then after that, we want to make sure that we are integrating different pieces together. So we have our data, we have our model, then we have various validation steps, and then we are generating a output, and then the output will go into production service. So we want to make sure that all these modules are stringed together. And then we also want to be mindful about experiment tracking. So here we mean both offline and online experiment. So at Spectrum, we're focusing primarily on offline experimentation because we want to launch things directly to the customer's hands immediately when we have something. So we do rigorous offline experimentation. We compare different model performance, and then we like evaluate different metrics, and then so like a lot of these functions are outsourced to weights and biases, which is a very great tool for like model development. And then we use workflows. So Argo is our choice, but you can also use like Airflow and whatever. So this is the integration part. And then after that, we want to make sure that we are putting the model into the prediction pipeline so that it is being served to the customer. And then also we want to be mindful about when to retrain a model. So there's like different philosophy there. Like you retrain a model once you see a drift in the monitoring process, or you can also retrain a model when you get new data. So we're going with the latter more because we're still getting very active label data coming back to our model, and then we're kind of in the phase that every batch of label data will actually help with the model performance. So we don't really need to let the model sit there until we see a drift, and then we go back to train the model. So there's like different phases that you're in, and then that decides what decision you make in this pipeline. So I kind of covered on this already. And then the following thing is, of course, resource management. Like a lot of these machine learning models require GPU to train. So like, for example, we have transformers that's being trained, and that will take about 2 hours on the GPU. And then if a single model uses that, the GPU costs maybe $30 to train a single model. And then we have, let's say, 50 models that we want to train, and then like, or even more, the cost will go up. So how do you manage to pick the right GPU for the data that you have, and then the model architecture you have, so that you can be cost conscious? So that's one definitely a big thing. And then we also want to be future proof about the adding new features to the model. So for example, the feature store, we designed it in a way that we have versioning, we have different split, but what's going to happen if, say, the data scientist or researcher decides to add 10 more features in the future? Can we actually afford that? So when you make design choices, you want to be mindful about this future variation of the product. So the last thing about this whole deployment process we're thinking is monitoring. So this is similar to what I mentioned before. So you want to detect model drifting and then or data drifting, and then what are the business KPI that you care about. So like for example, at Spectrum we care about precision. So if we automatically redact some of the chats that end users are exchanging to each other, are we right? Can we be right like 95% of the time, 90% of the time? So how can we monitor that? Those are, and also like, CPU usage, what is the count of predictions? Are we actually generating a distribution of prediction rather than just 0 and 1? So there's always a lot of things that you can validate in the monitoring process. So you always want to be mindful when you're building a pipeline. Yeah, so we recently launched the version 1 of this automated classifier training system. So it can actually kick off a training whenever there's a new data available. So we just grab the production model, use the same hyperparameter, but retrain the model on the new data. And then we'll go through some validation process, and then we'll launch the model directly into production. And then alternatively, data scientists can do whatever research they do, but if they have a candidate model ready to go into production, they will just use this automatic training workflow to launch a model directly into production. So it kind of just reduces the friction between data science and engineering. And then so again, like this decouples the work between model development and serving, so that it reduces the friction among like that life cycle. And then so this could also free up a lot of time for the data scientists to do more research, because if they were just manually trying to copy and paste the model artifact from staging to dev to production, it's not very efficient time on their hand. So we want to give them a lot of flexibility so they can work on adding new features, they can work on inspecting the quality of the data, they can work on inventing a new model architecture or training procedure. So yeah, so I'm just gonna give a quick demo to how this training workflow looks like as well. So it's very similar to the feature store. We have a classifier training tab, and then we can type in the classifier name, the version, the embedding name, and then there's a bunch of other parameters that we type. And then here we can specify the model architecture parameters. Those are just the key value pairs that will go into our internal tool. So like, for example, here you can say learning rate, epoch number, batch size, blah, blah. You can say anything. And then if you click experimental run, then it will now go into production. So this is for DS to offline test if they can actually generate an artifact that spits out prediction or not. And then if they click a submit the job, it automatically starts the workflow in the backend. And then you can actually see the results are generated from here. You see the directory of the data set, the embedding, the training run path, etc. And then like using the training run path, this is what you do to go to weights and biases, and then you can actually pull out all the information that weights and biases logs. And then on the very back end, this is the Argo workflow that the classifier training pipeline kicks out. So you can actually see it has different modules, and then make sure that everything is dependent on things that they need to be, and then it's all green check marks, which is great, and then it logs, and then we have a model artifact generated in our production directory, and then it's ready to be picked up by client traffic. So that's it for the classifier training. I am gonna pass it back to David to talk about how do we update our solution overall.
So after the classifier is trained, before it gets to production, we need to do some solution configuration and testing, which I'll describe now in the next step. So a solution consists of a classifier and its related rules and configuration is the best way to think about it. So those are packaged up as a unit, and it's basically a unit of deployment for a classifier when it goes to production. Before we deploy it to production, we need to run the solution against our train and validate sets, and also any customers that have licensed this particular behavior, we'll pull out some live traffic. We'll make sure that things haven't regressed for them. We measure performance and quality via some metrics. So previously, before we invested in this new process and pipeline that I'm going to show next, all of these things were done manually. Data scientists would have to retrieve the data themselves, they'd have to invoke the job, they'd have to generate their own metrics on their own machine. So it was a timely process, a lot of manual steps, and an inconsistent process too as well. So we'll show how we have built out the tools that now streamline this and make it a more programmatic workflow. So just to describe how we test out our solution. So we're using a tool called our DAP job. Our DAP job stands for Data Acquisition Pipeline. It's basically a job that contains the same classifier scoring runtime that we have in our production real-time APIs, except we can invoke it in any ad hoc manner. So typically what happens is you'll provide the solution along with some configuration to the DAP job and specify a data set that you want to score it against. So the DAP job will go to a model repository, retrieve the appropriate classifier that has been trained in the process that Jambo just described. It'll also go to our data vault catalog, retrieve the data set, and then score the data and eventually classify it into a result, which you'll see at the bottom where we got our input text, we got our human label, which I guess is the expected output. The behavior then is the actual output, and the score is the result from the classifier. So the rules of configuration will make up eventually what the output of the behavior is. So that's really the process that the data scientists will follow to generate the metrics, and then make a decision whether they need to iterate on this further or it's ready to go to production. A little bit about DAP itself and some of the technical details. So we run all our data pipelines on using a tool called Argo Workflows, similar to Airflow and those other tools that you might be familiar with. It's built natively on Kubernetes. So we stand up our own Kubernetes cluster, and within that, we have the ability to spin up and tear down our own Spark cluster. So what happens is we have when we invoke a job, we have some pre-processing that takes place. The classification takes place on the Spark jobs themselves. So depending on the size of the file that we're looking to score, whether it's 50,000 records or 50 million, we need to size that cluster accordingly. So because everything is stored in our data vault, which is a catalog, we know up front how many records are in that file, and then we can dynamically scale out that Spark cluster before we spin it up. So this allows us to proceed with an efficient batch-based process. I will do the questions after. Yeah, if you don't mind, we'll just do the questions after. So a little bit about Argo itself, very briefly. This might be hard to read now, but it allows you to construct workflows using YAML. So on the left, you've got a task. A task is basically a Docker image with an associated command. So your Docker image could be a third-party Docker image from Docker Hub, or it could be your own in-house repo converted into a Docker image. So in this case, it's a Python-based application where we provide a command, runs the application, and generates an output. On the right-hand side, a very brief snippet that shows you how you can construct many tasks into a DAG pipeline. In this case, the second task has a dependency on the first, and it specifies that it wants the output from the previous task as an input to its own task. So behind the scenes, Argo will take care of passing parameters and files, etc., around the place. Every task then executes. Every task and image creates a container which executes on its own container. So over the last year, we've gone on a usability journey to improve the process. Like this time last year, we probably had the ability to score ad hoc batch jobs. We didn't have the ways to query the APIs easily to retrieve data. We didn't have the way to figure out what jobs ran when. We didn't have any automation around the metrics reports, so we didn't have any notifications, which I'll describe in a second. So what we built over the last few months is a tool called Grogu. It basically is a user interface that sits in front of these other tools, like or collaborates with the likes of Data Vault, the data acquisition pipeline, etc., to provide a better usability experience for the data scientists and more automation. So in this case, what I'll show in the demo now is the data scientists will have the ability to query the data vault and the feature store to retrieve the data. They can then provide the configuration for the solution to Grogu. Grogu will then orchestrate the running of the DAP job. When the job completes, we get a notification via Slack. Then downstream, all the data is loaded into Snowflake, and we're using DBT, which basically manages SQL pipelines. We can generate automated metrics reports. So the data scientists now, after the job completes, they get a notification. They look whether, if it looks good, it's great, it's going to production. If not, they iterate through it further. So they're no longer refreshing UIs, doing manual operations, and they can invest their time in better stuff instead. So a quick overview of what the Grogu is about. So I mentioned the export APIs that we've created. So before this, a data scientist had to go into Snowflake, run a SQL query on very wide tables, figure it out, and then export that out into S3 using a copy command, which is a painful process. So we created the ability via some of these screens here where they can query any Snowflake table in our system, both our customer data and our scrape data. They can query for a behavior being true or false. They can query on a language, a classifier, a score range for a classifier, various keywords, and then hit export, and it will create an export of that data in seconds without them having to run any query themselves. We also have the ability to query our feature store. You can specify a behavior or lexicon name, the bucket type, also the version here as well. You have the ability to query for any particular version that you want. After that file, after you run your query, we generate an export. That export is cataloged in our data vault, and we have some metadata around it here. So for example, this the SQL that was used to create a particular query. So we have that bit of lineage. Then if you want to score that data, you can score the data and it'll bring you to our Grogu UI. So the Grogu UI, like I mentioned, allows us to validate our solutions before they go to production. So very quickly, I know we're running out of time here, we generate a prototype file which contains the configuration. We can specify a behavior, an email address for the Slack notification, then submit the job. After the job completes, you'll get a notification via Slack. You can then click on the details. To switch over here to one that I ran earlier, I think there's a. Oh, here we go. And you get these metrics for free. Lastly, a very quick overview of Argo. This provides a link to the Argo. Before we built out what we had, you just had a list of all your workflows in the Argo UI, but you'd no context to figure out what each one meant. So I'm just going to wrap it up now. I hand it over to Opman to give the conclusions.
What you probably noticed by now is that the data science team and the engineering team at Spectrum, they work very closely with each other, mainly to resolve pain points that we encounter, and really to scale up and make our kind of production of solutions very, very efficient. So actually, going through the categories I have, so very reliable. So anything that goes into production, there is a single source of truth for it. At any point in time in the future, we can reproduce any other solution that went into production from a single file. And the workflows that Yambo and David described today enable us to do that. It's easy to maintain. Instead of having code scattered across notebooks, across different code bases in people's laptops, now having these centralized workflows really like unify and make essentially producing maintaining solutions and producing them a lot more scalable. And then of course the lineage tracking that we talked about, either from the data side or the model side, the config that goes into the solution that gets deployed is all tracked and recorded and easy to retrieve. And then also like efficiency. So it's really streamlining the development process and then enable us to quickly iterate solutions. I mentioned earlier we had about 20 behaviors in 20 languages. This is a combination of about 400 pairing. And for us, that level of scale is very manageable with workflows like this, so that you really don't have to go through like essentially custom configurations. And adding more is very trivial at this stage. It's a matter of just kicking new workflow pipelines to like either train a new model or ingest new data in. And then, yeah, so which also play into like the swift deployment and basically rapid development of solutions. And then of course it's scalable as well. We can automate these processes. Later on, once we want, Yambo talked about ingesting data based on new data that becomes available. But later on, if we wanted to reuse drifts, then we can literally have an automated cycle that doesn't need any intervention if we wanted to. But this is really building up for scale and automation, and then expanding our offerings as we get new customers that want new models, and then continuously improve really our solutions and offer the best we can. So that's about it. We'll be happy to take questions. I know there was one question already. How about we start with that? Yeah. Maybe you can use the mic just so that we can hear you. Okay, sounds good.
Application like this, speed is like paramount. So I was just curious, like, what specific changes or like changes did you have to make in order to like have like really good speed and like just runtime with being able to label responses and things like that?
Sorry, good speed for what? Which part of the workflow you're referring to, or overall?
Just overall, yeah. Like with the entire just like pipeline and then even the feedback loop.
Yeah, so I mean, there are two components. Basically, the two components that feed into us triggering this workflow and generating a new solution is really either we proactively go and look at the billions of records that we have, sifting through data to find new trends that our current solutions don't cover. The other side of it is we get requests from our clients that ask us, we see, for example, these trends that are not being captured by your models currently. Can you investigate that? And that can trigger us to go and kick off these workflows so that we sample the correct data so that we cover these maybe like holes in our coverage. Does that answer your question? Okay. All right. So I mean, we are around, so feel free to grab any one of us to talk more about these technologies and what we do at Spectrum. But yeah, thanks for listening.